So I'm going to back up a little bit here because I realized I meant to record. Um, we're solving the classic projectile problem. We've got a golf ball that is hit at 50 meters per second at an angle of 30 degrees above the horizontal. And the question is, how far horizontally will that golf ball travel? And so we're going to find out the hang time of the golf ball. In order to do that, we had to break up this initial velocity into a vertical component and a horizontal component. So the vertical component, I'm going to go ahead and give the general equation. So this V0y would be V0 times the sine of theta, as long as theta is given with respect to the horizontal. Right, you all have done a lot of the trig here. So in this case, this would be 50 times the sine of 30. We're using sine because it's for the side of the triangle that's opposite the angle. And this is 25 meters per second. So this golf ball, when it's just struck on the tee, is moving a velocity of 25 meters per second up. Is it going to keep moving 25 meters per second straight up? What's going to happen? It's going to decrease because of the force due to gravity. It's going to accelerate downward at 10 meters per second squared. Horizontally, V0x is equal to V0 times the cosine of theta. That's equal to 50 times the cosine of 30 in this case, which is 43.3 meters per second. Okay, it's never a bad idea if you've got a projectile to break up. So the first thing you do could be to get the vertical and horizontal components of the velocity. Well, there are many methods you could use to get the hang time, approaches you could take, but there are two really good ones. Can you all think of one? What would you do? How would you get the total time in the air? Okay, so you're saying this one right here, this one right here, or this one? So if you knew the range, if you knew how far it went horizontally, you could use that to find the hang time. But we don't know that when we're trying to figure out delta x. The problem is we don't know t. And since the hang time for an ideal projectile doesn't really depend on what's going on horizontally, this equation could be useful. Okay, yeah, that's going to be my next question. So we could use delta y is equal to V0yt plus 1/2 gt squared. That works. So Grace says make delta y 0. Is that right? Yeah, I mean, what we're solving for is for the golf ball to return to its original height. So if the ground weren't level, then delta y would not be 0. But since it's returning to the original height it had, it's not a change. The delta y is equal to 0. Okay, so this is 25 times t plus 1/2 minus 10 t squared. Fortunately, that factors. So you get 0 is equal to 25 minus 5t times t, and you get two roots. You get t equals 0 is one root. It's one solution to this equation. The other one is given by 25 minus 5t equals 0. So t is equal to minus 25 over minus 5, which is 5 seconds. So, okay, easy enough and sounds reasonable. If you drive a golf ball with these characteristics, it's going to be in the air for about 5 seconds. It's a pretty long time. There's another good way to do it. Can anybody think of another way to do it? This other way does not involve a quadratic. So this delta y equation, we get a t squared term. The other way to do it does not involve a quadratic. Okay, let's write. I'm going to write that down, and then so yeah, we could use the velocity. It is possible to use the velocity equation. How would we use that? Yeah, exactly right. Yeah. So there is something that we know about projectiles. At the very top of the motion, right here, at its maximum height, at the v in the y direction is equal to 0. What about the horizontal velocity? Is at the top, is the horizontal velocity equal to 0? It's the same as when it started. The ball does not just come to a rest in the horizontal position. Gravity, the force of gravity brings it to a rest, but only in the vertical direction, not in the horizontal direction. So we could say 0.0 is equal to 25 minus 10t, but this would not be the hang time. It would be the time to get to the top. So the time to get to the top is minus 25 over minus 10, which is 2.5 seconds. Does it make sense to you if there's no air resistance that a projectile would take the same amount of time to get from the top to go back down as it took to go from the bottom up to the top? It is true. So to get the hang time, and this is an equation that you can use, you get as long as, well, I'll ask you, it's 2 times t to the top, but there's an important if there. What has to be true in order to get for this relationship to be true? Yeah, there has to be no air resistance, stuff like that. What also has to be true is that if delta y is equal to 0. It's not true if the projectile is like shot from the beach up onto a cliff or shot from the top of a cliff, down to something below. What has to be true is you have to have some symmetry here. It's like it's starting at ground level and going up to here, up to the top, and then going from the top back down to the same vertical position. There's symmetry there. So in that, you can use this equation in that case. So you get 2 times 2.5, which thankfully is 5 seconds. And so you get the same answer using each method. Either one is fine. You pretty much have to use this method, the delta y method, if the delta y is not 0, and then you get something that has 2 roots, like you have to solve the quadratic equation. But I'll put the quadratic formula back on your calculators if you would like it. It might come up, it will come up this unit. Everybody okay with that? Okay, so now how far, we know the hang time now. How far did the golf ball, what was the range of the golf ball? How would we figure out the range of the golf ball? Yeah, you say delta x is v0x times t, and so that's 43.3 times the hang time, which is 5.0 seconds, and I believe that's 216.5 meters. A couple hundred yards. So the last part's pretty simple. So what's different here from what you have done before is that you're dealing with x and y motion simultaneously. And that requires breaking up the velocity into a vertical and a horizontal part so that you can use those two separate sets of equations. You've got equations for the vertical and you've got equations for the horizontal. So let me see, I'm going to give you an opportunity to practice this. See if you can solve this problem. A water balloon is shot at an abandoned building. The velocity, the resultant velocity is 18 meters per second, and it's shot 50 degrees above the horizontal. And it's shot from a distance of 24 meters away from the abandoned building. I want to be politically sort of semi-correct. It's bad to shoot water balloons in buildings. So the question is, at what height will the water balloon hit the building, if it hits at all? It could, it's conceivable that it would go over the building. Maybe it hits the ground before it gets to the building.
can't use velocity.
Probably won't help you, yeah. Yeah. Well, there's a part B. You could use it to answer part B. But it won't help you to figure out part A, I don't think. So this is a bit of a different problem. Doesn't really help you to find the hang time in this problem, right? Mm-mm. Well, you can find the hang time, but you can't do it using information in the vertical direction. Can you find the hang time by using the information that you have about what's happening horizontally? Yes.
Why can you do it vertically?
Because you don't know that it hits the building when it's at the top.
So you know it's the building when the vertical velocity.
No, it doesn't. No.
Wouldn't it become zero once it hits it?
Okay, this is a good thing to bring up. The equations that we're using for projectiles don't know about collisions, you know. So it's like it's using those equations, it's like the building is not there. It won't be, there's nothing in those equations that will tell you, oh, it hit the building, so it stopped. It's as though it just went on passing right through the building. So the place to start off is this equation, right? That's where to start on this problem. So I'm going to go ahead and figure out the components. So there's the horizontal component and the vertical component. So the vertical component is 18 times the sine of 50, which I believe is 13.8 meters per second. Okay. And then horizontally, it's 8 times the cosine of 50, which is equal to 11.6 meters per second. Okay. Okay. So here's a question before we go any farther. Could you use, just a hypothetical question, could you use like a big ol' like honkin' triangle to figure out where the balloon hits the building and just do geometry with a triangle? Why can't you can't do that? Why can't you do that? Yeah, it doesn't move in a triangle. The balloon only has, the balloon does not continue straight on this path. It deviates from that path almost immediately. Instead of doing that, it moves in the shape of a parabola, something like that. So you can't use just do geometry. So this, that is incorrect stuff right there. So we have to use the equations for projectiles. So this would be 24. This would be 24 is equal to 11.6 times t. So t is equal to 224 divided by 11.6, which is like 2.07. Is that right? Okay, so it takes 2.07 seconds to reach the building. And now all we have to do is figure out the height, the height of the balloon when it hits the building. And we can just use delta y because 0 is the ground level. So delta y is b0 it plus 1/2 gt squared. So this is equal to 13.8 times 2.07 minus, well, so I'll do this, plus 1/2 minus 10 times 2.07 squared, which is equal to, I think it's 7.14. If you do all those numbers. So about 25 feet off the ground, something like that. You're okay with that? So what is a good way? Part B. What's a good way? The question is, at the time the balloon hits the building, was the balloon moving up or down? How could you answer that? Okay, calculate the velocity at 2.0 seconds. I think that's the best way to do it. But how does that tell you up or down? If the velocity is positive, it's moving up. If the velocity is negative, it's moving down. So that's not too bad. So we would say Vy is V0y plus GT, and V0y is 13.8 minus 10 times 2.07, and I think that winds up being minus 6 point something. Does anybody have it? Meters per second. So the negative tells us that the balloon was moving down. Okay. Not too bad, right? I mean, you all know these equations. You've used them before. Just might take a little bit of remembering, but it's kind of good to circle back and do it. So if there are no questions on this, then I'm going to go ahead and go. I want to talk about the lab that you're going to do on Wednesday. Have I told you anything about the lab you're going to do on Wednesday? Other than that it's on Wednesday. I think I could remember 30 minutes later. Okay, so this lab sometimes causes students some stress.
I can guarantee you some freaks out. Yeah. I can do.
So, do you want me to tell you the stressful part at the beginning, or do you want me to tell you
Yes. Beginning.
up front, just get it over with?
It's gonna be like it's due Thursday. That's what it's gonna be.
Okay, so here's the stressful part. Your lab grade will depend on your accuracy. And you only get one shot.
What?
Yes, you can always ask.
Oh, wow.
So it's not as bad as so that made it sound really bad. So here now this may not make it any better. It's bad, and it's probably not going to get any better. So um, you can only lose 10 points because of inaccurate data. So if you mess up the accuracy part of this completely, really badly, you can do a good job on your write-up and still get a 90. Okay. So here's what I'm going to ask you to do. There's going to be a ball, a steel ball, that is rolling across the lab table. You're going to make measurements. I'm going to give you the tools. I'm going to set everything, most everything up. I'm going to give you the tools to make accurate measurements of the ball's velocity. And you can measure whatever else you need to measure. Right? You can make as many, you can do many trials and all that kind of stuff without the ball ever leaving the table. I want you to predict that if you did not stop the ball from leaving the table, where it would land. And there's a clever way to do that that's very accurate. Basically, you're going to put a line on a piece of paper and you're going to say the ball is going to land on that line. And I have a way of marking how close it is to that line. Okay, when it lands. It's sort of like, you know, a clumsy way to do it would be to put like paint on the ball or something. And then when the ball hit the paper, it would leave, you know, a paint mark or something. So you're going to put a line down on the floor and you're going to say the ball is going to roll off the table. It's going to land here. But this is not an experimental side. You know, it's not like an empirical thing where you let the ball just go and you went, oh, it landed there. So I say it's going to land there on the next trial. You have to make measurements on the table. And based on those measurements, you make a prediction and you get one trial. And it's -1 up to 10 for every centimeter that you miss by. So, what? No.
And wait, how big is this spot that we get to pick?
It's a line.
Oh, it's not like a little circle.
Oh yeah. So what you're gonna do is you're gonna like put something on the table to keep the ball from rolling off the table, and you get to roll it as many times as you want and make sure you've got repeatability and all that on the table. Like people generally get to within 3 centimeters. Like I will just tell you, it's rare for a group to get more than 3 or 4, maybe 5 centimeters away. So there's some people who just nail it and get the ball to land right on the line. Just bang, it's just really amazing when that happens. And there's a little bit of rationale for this. There are times in your career, especially if you're doing engineering or science, where you really do only get one shot. You have to get it right. It would be really bad if you like got 80% of the way done building the Golden Gate Bridge and went, oh yeah, forgot about that. Like that's not going to be strong enough. Let's just start over. Like you can't do that with some things. There was a Mars probe that was sent off 20 or 30 years ago. One of the engineers on that project didn't convert from inches to centimeters. And the probe did not go anywhere close to Mars. It's in the universe somewhere. Completely missed. I don't know how much that cost, but it was not cheap. You know, somewhere like $100 million, boom. Mm-hmm. I don't think you could probably sue them. It wasn't like malintent.
Is the lab a group lab or?
It is a group, so you'll pair.
Oh, so I might need like race or something for this.
Okay.
I'm kidding. Yes. We're partners.
You're saying it's
So
within
we're gonna do
centimeters, like
I have never had a student try to take into account air resistance in any kind of formulaic or structural or with calculations. And everybody has generally done just fine. The only time that people have really messed up, I'll give you examples that where people, the reason that people mess up. Like during the part where you're gonna, to start the ball in a repeatable fashion, you're gonna roll it down a ramp. And so you pick the starting point on the ramp, right? And you get a ruler at the starting point in the ramp and you practice it. You know, it's like, okay, when we release it from here, the velocity is reliably this much. It's this quantity. And then they'll do that 10 times. You know, I'm exaggerating. Most people only do it like 2 or 3 times or something. But they'll do it many times, multiple times from that place. And then they go, okay, this is for real. And then for some reason, their brain just wipes. And instead of doing it from the same place that they've been doing it, they do it from somewhere else on the ramp.
So the ramp could be like a ruler or something?
Yeah, it's got marks on it. And the other reason that people will mess up is often units.
Oh, they'll measure and say.
Just like the engineer who messed up on the Mars probe calculation. So a good thing to do right now, at least before Wednesday, is to solve this problem. So for here, given that you have a ball that's rolling 2.4 meters per second and that the table is 60 centimeters high, solve for delta x.
It's not like it.
No. So I haven't posted the notes on, I haven't posted any projectile notes yet. Victoria is still laughing over there.
Oh, you already showed us your answer.
Yeah, I'm going to give you the answer for this particular situation, just so you know if you got something wrong. In the real deal, though, I don't know what your answer is. I'm not going to be able to tell you if the number that you come up with is correct or not. I don't know where it's going to land.
So, can you tell us how many centimeters until it falls off? The table?
Well, it's the velocity when it goes off the table is 2.4. So one of the assumptions that you're going to have to make is that the velocity that you won't be able to measure the velocity of the ball when it's right at the edge of the table, but you'll be able to measure it just before it gets to the end of the table. And the assumption is that since there's not a lot of friction on the calculator chaos over there. That would be good. We should just, like, if we had a visitor one day, we could just all randomly start dropping our calculator. Whoa. Those were like miserable times for me. Oh my gosh. It's obviously they're fun times too, but oh man.
Yeah, I wrote 60. Wait, how many stems? Is it 100 centimeters?
Yeah. You just finished what? Oh.
Well, VX.
Oh, wait, this is not bad.
You'll figure it out.
You find the time it takes to go in vertical direction.
You already
use
do
that
it.
same time to find the displacement, and you already know horizontal.
Mhm. You already do it?
Oh, wait.
I got 0.83.
I mean-
0.831.
I don't know what to do. Oh,
But it's because I use 10 instead of 9.8.
okay. Here's an important point about the lab. Because in the lab, you care about accuracy. What are you gonna use for the acceleration due to gravity?
9.8. Negative. Correcting it, same placement.
Yeah,
9.8.
yeah, that's a good one. Don't freak out. We'll get Miss Forrester to come in and do a.
Is this really all it is? Is it just part of it? So there's no need.
I don't think so.
The only thing is you have to be able to push it to stay at the same velocity every time.
Which you can do because you're not going to push it. You're going to put it up on certain distance up a ramp. You're not going to change the ramp. And you're just going to stick a ruler there and then move the ruler out of the way.
Square root, square root of 20. Because it's 60 centimeters, not 60 meters. So 0.6 meters.
Do you get it, Kenny? Let's talk about it before you leave. Unless you want to wrestle with it. Okay. Okay. The what? Okay, that's a good question. If something is rolling, like when it's on the table, what's the vertical velocity? So the instant that it comes off the table, there hasn't been any time for it to change, so the vertical velocity is
What do you use negative
Zero.
10 versus we went to the lab and negative 100.
Yeah. The initial vertical velocity. So when it first becomes a projectile, it hasn't had time to fall, so the velocity is zero. The vertical velocity is zero. When it's rolling on the desk, the vertical velocity is zero. With not moving down initially,
Why are you bringing pain?
it's moving with the same velocity it had when it was on the desk at the very beginning. Now, over time, the vertical velocity it falls, and the vertical velocity gets more negative, a bigger and bigger negative number. But initially,
Wait.
no, because this equation right here, that's where it starts. But over time, it changes. When it first comes off the table, the vertical velocity is zero. So, okay.
Doctor, how are we gonna calculate velocity?
I'm going to give you some photo gates. They're electronic devices.
That's how we calculate velocity. Thank you, Doctor.
See you, Daniel.
It was so bad. Yeah. I know. Yes, we so much. I know.
Thank you.
Okay. Okay. Yeah. Oh, where there's an energy part and there's a number 9 in the multiple choice is kind of a good one for that. Well, not really. Number 9 in the multiple choice is a good problem. See you, Henry. Have a good weekend.
I feel pretty good about the problem that you're doing. I'll look at it a little bit. I might get on to
Okay.
email you or maybe-
Sure. Yeah, I'll try to respond.
Okay, and I might just come in.
I mean, it's nice because we have Zoom now, so if you let me know enough ahead of time, I can probably send, I can, do some. Okay, all right, sounds good.
Thank you.
See you, Sloan. I
I
know. Are you okay? Is your car like?
Yeah, it was his car, but his car's fine and everything, but he just had to like deal with the people and it's like all longer than
It's not a problem. It's not a problem. Oh, you know what? I'm gonna stop this so that
What do you have to have like when you get in a wreck?